Have you ever wondered what the area under a bell curve is? Probably not, but it's something very interesting. If you're using this in probability, it should be normalized, so the area should be 1. Otherwise, you can have probability greater than 1 of something happening, and that's not okay. However, the basic shape is made by the function f of x is equal to e to the negative x squared. So, and actually, in order to normalize it, you have to know what is the area under that, so the probability will work. We can divide by it afterward. So, what is it? And it's actually a very interesting answer that connects probability and circles. So this is going to be the area under the bell curve, this integral from negative infinity to infinity, and I'm just calling it I, it's some number. Now, the cute trick here is that I squared is equal to 2 of these multiplied together. Where here I'm using y instead of x because it's just a variable of integration, so it doesn't matter what I use. But we can combine these by multivariable calculus tricks into a double integral, which is going to be e to the negative x squared and then minus y squared, or if we factor out a negative 1, e to the negative x squared plus y squared dx dy. So this is the square of our area. Now, at first it looks like this makes it more complicated instead of less complicated, but not so. Let's talk about polar coordinates for a second. So if we have a point x, y on the plane, and we draw from the origin this right triangle here, this makes an angle theta with the x-axis, and then this distance from the origin is r. So we have a transformation that we can make in terms of x and y and r and theta so that we can use polar coordinates r and theta to specify a point instead of x and y. So r, by the Pythagorean theorem, r squared is equal to x squared plus y squared, and theta is going to turn out to be the inverse tangent of y divided by x. So that's how we get in between them. Actually, there's an inverse transformation too. So let's just give that. X is going to be equal to r times cosine theta, and y is going to be equal to r times sine theta. So this is how we get back and forth between Cartesian coordinates and polar coordinates in the plane. Okay, so now what we'd be interested in doing is, you see how this x squared plus y squared is also equal to r squared in polar coordinates. Let's try and change variables. Now, what we're going to have to do is we're going to have to change the limits, the variables here, and the differentials here at the end. So each of them is going to be its own battle. So negative infinity to infinity in both the x and y directions is going to be the entire plane. What's the entire plane in polar coordinates? Well, it's going to be once around the circle, so 0 to 2 pi for theta, and 0 to infinity, you can't have a negative distance from the origin, for r. So 0 to infinity. Then we substitute r squared for negative x squared plus y squared, and now we just have to figure out what is dx and dy in terms of dr and d theta. It's not just dr d theta. So the way we're going to do that is we are going to recall that the dx is going to be equal to the partial derivative of x with respect to r times dr plus the partial derivative of x with respect to theta times d theta. In this case, partial derivative with respect to r, we're going to get from this formula, is just going to be cosine theta. And then with respect to theta, we're going to get negative r sine theta times d theta. Similarly with y, we're going to get derivative of y with respect to r dr plus derivative of y with respect to theta d theta. And this is going to be none other than sine theta dr plus derivative with respect to theta is just going to be r cosine theta d theta. Now, how do we get dr and d theta out of this? Well, what we're looking for is a substitution for x, dx and dy. So we're just going to multiply these two expressions. Sometimes it really is that simple. So dx, dy, our area element in the plane, is going to be equal to cosine theta dr. I'll just bring out the minus sign here. Minus r sine theta d theta times this expression, sine theta dr plus r cosine theta d theta. This is going to be equal to, once you multiply all the terms, we're going to get sine theta cosine theta dr, dr is the way I'm going to write this for the moment. Let's do the last terms next. Minus r squared sine theta cosine theta d theta times d theta. Now the mixed terms, plus sine theta, actually let's do this, minus r sine squared theta d, and this order is going to matter, so we want to write it from left to right, d theta dr, and then this last one, which is going to be here, plus r cosine squared theta dr comes first, dr d theta. Now we can actually switch dr and d theta, and the effect that has is that this becomes positive. And then by the rules of differential forms, gotta love them, dr times dr is 0, and so is d theta times d theta, so that this bottom part is all we have. And then if you just factor out r dr d theta, you'll get sine squared plus cosine squared, which is 1. So this equals just r dr d theta. So this is our area element for the plane in polar coordinates. So I'm going to write our integral in terms of this. So here we have our integral written in polar form. Now this r here, along with the r squared, is going to allow us to make a substitution. So let's set u is equal to r squared, du is equal to 2r dr, or if you like, r dr is equal to 1/2 du. All right, let's make that substitution. What are we going to get? We're going to get the integral from 0 to 2 pi, integral from, what are our limits going to be? When r is 0, u is 0. When r is infinity, u is tending toward infinity. So we're going to get e to the negative u times, and then the r dr comes out, and instead we get 1/2 du, and then d theta. I'll write this over here, and this is going to be, we can pull out the 1/2, 0 to 2 pi, and then the integral of e to the negative u du is just going to be negative e to the negative u, evaluated at 0 and infinity, and d theta. And this is going to be none other than we could factor out the negative if we want, and it's going to be e to the negative infinity, which is just going to be 0, minus e to the negative 0, which is just going to be 1. So this is going to be a minus 1. These end up canceling out. So then we just have d theta. The integral of d theta from 0 to 2 pi is just going to be 2 pi. So 1/2 times 2 pi is equal to pi. Now, keep in mind this was I squared. We use the square of this number that we're looking for to find this. That means that I, the actual area under the bell curve, is going to be equal to the square root of pi. Interesting how pi should come up with bell curves, huh? Isn't that a cute little trick? It's a classic. It's called the Gaussian integral.